We present a framework for doing motion synthesis and editing using deep learning. Deep learning has seen great success in tasks such as image classification and speech recognition, but it's only recently that researchers are finding ways to use it for synthesis. We present a method for performing motion synthesis and editing using deep learning which is simple, fast, and does not require any manual processing, labeling, or segmentation of motion data. We start by building a motion manifold using a convolutional autoencoder trained on 20 hours of raw motion data. Then, given parameterizations such as the trajectory of the character, we can train a deep neural network that maps to the top of the autoencoder and output motion which corresponds to these inputs. As the input trajectory does not fully specify the motion, doing a naive regression results in the potential outputs being averaged, causing the character to appear to float. We therefore train a small neural network to disambiguate the input trajectory using the foot contact information. After this, the raw output from the feed-forward network is very fast to compute, but may not exactly follow the trajectory and may exhibit other issues such as foot sliding or variations in joint lengths. Post-processing using inverse kinematics can fix some of these issues, but doesn't enforce any temporal continuity or realistic posing, and so may produce jittery motion or joint popping. Instead, we use the autoencoder to learn how to naturally edit the generated motion. We formulate the editing task as an optimization problem over the space of the autoencoder's hidden units. Editing the motion in the hidden unit space ensures the edited motion is natural, as it is adjusted along the manifold of valid motion. We now show some more results. By making the character face sideways, we can naturally produce sidestepping motion. And by varying the velocity, we can introduce transitions. We can also use different parameterizations. Here the user specifies the movement of the hands or of the feet, and our system generates appropriate punching and kicking motions. Further arbitrary motion edits can be applied. Here we edit some walking motion by constraining the character's hands to move in circles. Here we edit some running motion such that the character picks up objects from different locations and at different heights. Here we edit the motion of a character to step on pillars of different heights. Very high-level abstract motion edits can also be specified. By constraining the gram matrix of the hidden units, we can construct motion with the style of one motion and the timing of another. This allows us to perform style transfer without any alignment of the two motions. Here are some of our results. Our method can run on the GPU in parallel across the timeline. This makes it very fast and therefore perfect for crowd animation. Here we generate 10 seconds of motion for a crowd of 200 characters. This takes 1.8 seconds with motion edits applied and 2.2 seconds, for a total speed of 30,000 frames per second. In conclusion, we present an end-to-end framework for motion synthesis and editing which is fast, powerful, parallel, and unlike existing techniques requires no manual processing of data.